This video is going to be a review on Newton's law of universal gravitation, and the idea being that any two objects that you have are going to be gravitationally attracted to each other, and that there's a formula that we can use to calculate what the force of gravity is between any two objects. So it goes like this. The force of gravity is going to be Newton's gravitational constant, which we just write as capital G. And then we have mass 1, mass 2, and we divide it by the distance between them squared. I think we'll often see a negative put out in front of this, just depending on kind of reminding you that it's an attractive force. So if I have my two objects right here, here's my mass 1, here's my mass 2. This r is the distance between them. I kind of wish that this was listed as a d instead of an r, but that's just generally how it's known because r makes me think of radius. But it's really the distance between my objects, mass 1, mass 2, and then this g, this constant g, is just something that you are going to be given in a formula page on the AP test. It happens to be that g is 6.67 times 10 to the negative 11th, and then the units on it are newtons meters squared per kilogram squared. So that just makes the units of force work out to be in newtons. So these force units will be in newtons. That's kilograms, that's meters, and then this is newtons. The meters squared cancels out the meters squared on the bottom, and then the kilogram squared cancels out the kilogram squared for the top up here. So you can just have basic problems where you're just plugging in numbers and figuring out the force between things. So that's one way that this is used. Another way that this is sometimes used is in thinking about problems with the Earth. So if we have our Earth right here and maybe we have our cow or whatever the object is that's sitting up here, we often like to talk about the force of gravity that's acting on something. Now, when we usually have F with a big G right here, we're talking about this full Newton's law of gravity like this. If we just have something that's kind of close to the Earth, then we often will just write it as m times g. But there's a couple of assumptions that we're making right here. This m is actually the mass of this object right here. So that's the mass of this object. And then this g is assumed to be for the Earth. We know that it's close to the surface of the Earth, at least 9.8 meters per second squared. But we can actually use the full Newton's law of gravitation equation to figure out what the force is going to be here. So what we actually need is the distance from this object all the way to the center of the Earth, like that, so that we can have this be our r distance right there. And then my masses, I'm going to have the mass of the Earth right there, and then I'm going to have this as the mass of my object. So that's the mass of the object. And then if I want to find it out with Newton's law of gravitation, then I get F big G is G, and I have mass of the Earth times the mass of the object over the distance between them squared. So that's how that's going to work. Interestingly enough, this should be the same as this. It's the same force, right? It's just one of them is calculated using this little g and one of them is calculated using this, but these two things should be the same. So I can actually equate them together. So I could say this, g, mass Earth, mass of your object divided by the radius squared is mass of the object times g. And what that means is that if I take the mass of the object out, then g, what little g is really equivalent to, is g times the mass of the Earth divided by the radius of the Earth squared. Now, technically, I should have it as the radius of the Earth plus this distance right there. But since we say that when we're using this mg right here, it's close to the surface of the Earth, my diagram here is really, really off. So we're so close to the surface of the Earth that the difference between the object to the center of the Earth and then the surface of the Earth to the center of the Earth, that's pretty negligible. So this little g right here means close to, where is it ready to go? This little g right here is close to the surface of the Earth, so this r is really just getting you to the surface. So my diagram was a little bit off right there. So that's what this little g really comes from. And for a different planet, then we would just need to stick in the different mass of the planet right there, or the moon, or whatever you want to stick right there. So this g that we call 9.1 is Newton's gravitational constant times the mass of the Earth divided by the radius of the Earth squared. But put in any planet that you want here and you can find g on that planet, right? Okay, so that's one thing. The other thing that often comes up on the AP test, let's see, where should we go here? I'll just flip this over, is the concept of potential energy. So we have our senior equation, UG, being mgh, right? But if we, this is going to be close to the surface of the Earth, but if we want to, we can actually stick in kind of our new value for here for g. Oh, by the way, this is going to be the mass of the object, right? Since we're talking about objects at a certain height above the surface of the Earth. So, and then this g, of course, is for the Earth. So if I just flip back over here and, remind us what g is, that's big G times the mass of the Earth divided by the radius squared. So let's stick that in back over here. So we're going to remake this UG equation. UG is going to be the mass of the object, and then this g right here is g, mass of the Earth divided by radius squared. And I'm going to turn this height here into radius, because we can actually figure out for this formula, kind of a general formula for gravitational potential energy. So what's going to happen here is our equation for UG is going to be g, mass of the Earth, mass of the object, divided by just r, since one of those r's is going to cancel. So this is the gravitational potential energy between any two objects. Oh, sorry, I'm going to make it more general by UG is, g times m1 times m2 divided by r. Now there's something missing from here, which is a minus sign. So I'm just going to go ahead and stick that minus sign in there now, and then we're going to figure out where that comes from. But this formula here is saying if I've got two objects, mass 1, mass 2, and they're separated by a distance, stay there, stay, separated by a distance r, then this is the gravitational potential energy between them, right? G times the mass of 1 times the mass of 2 divided by r. Now why is it this negative number right here? Well, what we really need is we need to kind of figure out a definition for where zero potential energy is. So let me refer back to our Earth equation real quick. So on Earth, what we're doing is with this equation, we're saying, here's the surface of the Earth, and here's your object, some distance above the Earth, and that's your height right there. And what we're saying is that at ground level right here, that your potential energy is zero, right there. But when we come down to this formula right here, it actually works a little bit different. Because of this negative number right here, what we're actually saying is that when objects are an infinite distance apart, that's when they're going to have zero gravitational potential energy. And as they get closer and closer together, their gravitational potential energy is going to get less and less negative as it's getting closer together. So we want the gravitational potential energy to be increased as they're closer together, but we kind of need a 0 point. And the 0 point doesn't make sense for them to touch because you're never going to get two objects to touch. There's always going to be a little bit of distance between them because these are physical objects, right? So what we need is to set our new gravitational potential energy 0 point at infinity, and that's kind of why this introduces this negative sign right here. So what is that going to look like in terms of a graph of things? Well, if I graphed the gravitational potential energy between these two objects right here over distance, right? So it actually needs to go negative. So here's the gravitational potential energy compared to the distance. It's actually going to look like this, so that as r goes to infinity, my gravitational potential energy comes to 0, and that at 0, kind of, if I could get these objects to touch each other, which I really can't, then this is going to reach down like this. So here's a graph of this potential energy. This will be a real common AP Physics question to come up, something like that. The other way that this might work is if you actually talked about a planet. So let's say we had the Earth, and you just had some object kind of hovering above the Earth, and we wanted to graph its potential energy, say from the center of the Earth out. This is something we hadn't covered, but this graph is going to look a little bit different, sort of similar, but while we're inside the Earth here, the gravitational potential energy is going to be starting at 0 here. It's going to increase in the negative direction until it gets to here, and then it's going to decrease as it comes up like that. So I'm just showing you this. This requires a little bit more than just 30 seconds of time right here. But so I'm going to put on this r-axis right here, I'm going to put the radius of the Earth like that. So this graph is going to look like this. It's going to increase until it hits the radius of the Earth, and it's going to decrease like that. So if I took my object and I started it at the center of the Earth, obviously pretty hard to do, its gravitational potential energy is going to get bigger and bigger and bigger and bigger until it hits here, and then it's going to get smaller and smaller and smaller up like that. And this is bigger in a negative direction and then smaller up like that. So once again, this is sometimes comes up on the AP test. This is sort of a common thing to come up on the AP test as well. Yep. Let's see, the last thing is I wanted to just talk about Kepler's laws. So if I can get myself some space back here. So Kepler's laws might come up, especially Kepler's third law. So let me just talk about them sort of quickly here. Oh, let's see, there's one more thing that I wanted to talk about after Kepler's laws. So let's talk about Kepler's laws. Kepler's laws are going to be for orbits. So if I have a planet and then I've got a moon that's orbiting around the planet, or I've got the sun and I've got the Earth orbiting around the moon, things like that. So there's 3 laws. The first law says that the orbits are ellipses, so that they're elliptical. So a circle is an ellipse, by the way. So a circle would be an ellipse with an eccentricity of 1. I think that's how it goes. So they're nearly circular, the planetary orbits, but they are ellipses in general. I don't think that would come up as a question on the test. The second law is what we call the law of equal area. That means that in a given amount of time, if I have my moon and I say the moon goes from there to there in a given amount of time, and I figure out how much area is in this sort of triangle-y thingy right there, and I pick any other points on the orbit and I have the same amount of time, so that the time it takes to say go from there to there, if this is the same amount of time as this, then this area is going to be equal to that area. So yeah, once again, I don't think that's going to come up. But the third law might come up. And the third law says this, that the period of an orbit squared is going to be proportional to the radius of the orbit cubed. Now, I don't know how you're going to remember that, but that just might be something you have to look at a bunch of times and just remember that. So what that means is that however much time this whole orbit takes to go around is going to be proportional to the radius. So if you had a bigger orbit further away, then it's going to take more time to go around, but they're not linearly related. In fact, it's this weird t squared equals r cubed kind of thing. So if I double the radius, the period's going to go up, but it's going to go up by a factor of 3/2 or 2/3 or something like that. Anyways, so this is the Kepler's third law, and that might come up on the AP test. I'm not totally sure, but it's very possible. If it did, it would be a pretty basic thing, and if you missed it, then that's not that big of a deal. One other thing I wanted to talk to you about for orbits, if we have a circular orbit, then we can actually do some kind of pretty interesting calculations right here. So let's say, oh, there goes my lights. So I'll turn the lights back on. Okay, so we're going to have a planet, and then we're going to have an object orbiting around the planet like this. Just like that. Good. A satellite, a moon, or whatever it is. And we can have a couple of equations that we can think about. First of all, if things go in a circle, then what we know is that they need a centripetal force acting on them, and that's going to be m times v squared over r. So if this is going in a circle, this is the force that I need in order to go around in a circle. Well, where am I getting that force from? Well, I'm getting it from the force of gravity, Fg. I'm going to use big G right there. So my force of gravity is G times m1 times m2 over r squared. This is how much force I need, and this is how much force I'm getting, so I should be able to equate those things, right? So I should be able to say m times z squared over r is g m1 m2 over r squared. Now let's talk about what m's we have right here. If I really wanted to make it kind of a little more clear, then this m right here, that's the mass of the object. So this m right here, I'm just going to call that the mass of the object, and that's the mass of the object that's orbiting around. And then this m2 over here, that's going to be the mass of the Earth, which I'll do a capital E this time. So once again, there's two masses here. I've got the mass of this thing, and I've got the mass of the planet down here. So I'm just calling m1 the mass of the object. That's the same as this mass over here, because this formula is for the thing that's going around in a circle, not for the thing that's being circled. So now I can start to cancel some things and do some interesting stuff. So I can cancel that m. and I can cancel that r with one of these r's, and then I get this kind of cool formula here that tells me how my velocity is going to be if I'm in a circular orbit. And it's v equals the square root of g times the mass of the Earth divided by r. Now, of course, mass of the Earth right here could be the mass of anything that's being orbited. It could be, this could be the mass of the sun, if you're orbiting the sun, whatever this is over here. Notice how the mass of the object is not involved right here. And what it also says is that the higher up you are, the slower you go. So if this number gets bigger, this number gets smaller. So if I have an orbit, a circular orbit that's further away, then my velocity is going to go down. That actually comes into play up here as well, that if this number gets bigger, remember that's the radius, where we're saying if the radius gets bigger, the velocity gets smaller. Oops, where'd it go? If the velocity gets smaller, radius gets bigger, velocity gets smaller. And if my velocity gets smaller, then my period's going to increase because I'm going slower. It's going to take me more time to get there. So these are kind of related to each other, right? So that's sort of the basic ideas behind gravity. It'd be great to do some practice problems in there as well.